In your booklet, it should be page 4. If you haven't opened it yet. So how many times have we seen transformations this year? A lot. Pretty much through every unit. Okay, it's very important. And it's very important you know what A, B, C, and D mean. They're not just letters of the alphabet. Okay, so horizontal transformations will come from B and C, and vertical transformations will come from A and D. What does parameter B do? Okay, right here.
Stretch.
Horizontal stretch. What do we have to remember? Take the reciprocal. So it's by factor 1 over the absolute value of B. Now if B is positive, yeah, we have a horizontal stretch of 1 over absolute value of B. But what about if B is negative? Exactly, we have a horizontal stretch of 1 over B, but we also have a reflection over the y-axis. Okay, parameter C. It's inside the brackets. If it is not factored away, right? If, say for example, if we had y equals 2x plus 4, and then squared plus 5. Okay, what do I have to do with this 2 first? Factor it out. Okay, so just always make sure you're factoring out the stretch factor first, and then we can look at that individual C parameter on its own. Now what does C tell us? It's a horizontal translation. In this case, we'd be moving left 2 spaces, but if we look at the transformation equation, there's a negative there. So the value that we subbed in was actually a -2, which is why we're left. Okay, so if C is positive, we move right. But if C is negative, we move left. And overall, this is a horizontal translation. And we're going to go through a few examples later where you're seeing when it's positive, when it's negative, which way to move. Okay, so looking at the horizontal factors, parameters, basically that's what's going to affect our domain. Okay, so if you just look before, which parameters affect our domain, that's going to be the B factor and the C factor. We also have some vertical transformations starting with A. A is always going to be in front of the original function, and that's a vertical stretch. Okay, by factor A. So whatever A is, that's what we're stretching by. Okay, if A is positive, we have a vertical stretch by A. But if A is negative, we have a vertical stretch by a factor of A, and we have a reflection over the x-axis. So if you're asked what the vertical stretch factor is, you wouldn't say it's like -3. You would say it's a vertical stretch by 3, and then you would further describe there's a reflection over the x-axis. Okay, parameter D, it's always outside of the function as well. It's added to that function or subtracted. That's our vertical translation. And depending on whether D is positive or negative, we're going to move up or down. So if D is positive, we move up, and if D is negative, we move down. So which parameters will affect the range? Just looking below. Okay, that's going to be parameters A and D. Okay, so say we have y equals f of x, and we are transforming to y equals a times b, or sorry, f of b of x minus c plus d. We're going to be constantly dealing with point mapping, so I'm just going to give the general notation of what we would do. Okay, that means our points x, y would go to, let's first look at the x values. Okay, remember our stretch factor is 1 over b. So x will be transformed to 1 over bx, okay, plus whatever the c value is. And our y coordinate will transform to our vertical stretch a times the y value, and then whatever d is, we're going to add. Okay, so that's the general notation for point mapping when we're dealing with transformations. We have a few specific examples that we're going to touch on later. Question?
I thought like if C is like, if it's negative, like you go to the right.
So if c is negative, then we move to the left. Here, c is equal to negative 2. So if c is a negative 2, we move to the left. But in the equation, it looks positive, right? We have x plus 2.
Okay.
This means move left.
Oh,
Does that make sense? Okay. So in the equation, yeah, if it says x plus something, we're moving left. But the actual c value was a negative 2 because of the notation. It's x minus negative 2. Minus minus gives us the positive. Okay.
So when you put the point mapping, when you put the value of C in?
Yeah, so whatever the value of c is. So if c was negative 2, well, we're moving left 2, right? So we have to subtract 2. And we're going to do a few examples from this later.
If it's x plus 2, the value of c is negative 2.
Yes, yeah. You got it. Like I said, we're going to do lots more examples. So just hang tight for some point mapping examples. We also looked at in the transformations unit, as well as the functions unit, inverses, or reflections over the line y equals x. Okay, so when we're finding the inverse, what happens to the x and the y? They switch, they're exchanged, okay, as well as the domain and the range, they switch. So why don't we just give an example here, and we'll find the inverse. Okay, find the inverse. And its domain and range of y equals x squared plus 3. Maybe I'll just put and. So find the inverse and its domain and range of the original graph y equals x squared plus 3. So this is a reflection over the line y equals x. In order to solve for this algebraically, we start with the equation y equals x squared plus 3, and we exchange the x and the y. Okay, so now we have x equals y squared plus 3. Our goal now is to isolate the equation so we have a y equals equation. So subtract 3 over, we get x minus 3 equals y squared. Then we need to square root both sides. What do I have to remember when I square root both sides? Plus or minus. Good. So my inverse will be y equals the positive negative square root of x minus 3. So let's take a look at the original graph, x squared plus 3. That's a parabola that looks like this. Okay, this point here is 0, 3. When I look at the inverse, what happens to all the ordered pairs on the graph? They switch. So what's this point now? 3, 0. So 1, 2, 3, 0. That's going to be the vertex of our inverse graph. Okay, and it's going to look like this. Is this a function?
No.
Why?
It's a negative square root.
Because of one of the pieces of this square root. Yeah. Okay, so whether it's a positive or negative piece, when we do the vertical line test, we're crossing through 2 points, so it's not a function. Okay, we're going to have an example later where we can restrict the domain so it is. But for now, I just wanted to point that out, because if this question started out as f of x, another notation for inverse is this, right? But we can only use that notation if the inverse is in fact a function. This is not a function, so I cannot use this notation. I have to leave it in the form y equals, okay? So just be aware of the notation restrictions. Okay? This is not a function. Now let's talk about domain and range. It's probably easiest to look at the domain and range of the parabola first, and then we can talk about what's happening to the inverse. Okay, so the domain for the parabola x squared plus 3, x values, going forever to the, which way am I facing for you guys? The left, and then forever to the right. Okay, so x is an element of all real numbers. Okay, for the range, y has to be greater than or equal to this point here, which is 3. Everything else will be real numbers. So for the inverse, y equals positive or negative square root of x minus 3. What's going to happen? Well, the range becomes the domain, and the domain becomes the range. So the domain is now x is greater than or equal to 3, where x is an element of all real numbers. Okay, just like we see in this picture here, x is going to the right of positive 3, so it's greater than or equal to. Okay, y is going forever up, it's going forever down. So look at the switch, domain becomes our range. Our range now is y is an element of all real numbers. So just keep that in mind. It's sometimes easier to find the domain and range of the original function and then switch it, rather than finding the inverse and then trying to figure it out. Okay. So for example, if you weren't asked to find what the inverse equation was, you were just asked to find the domain and range of the inverse, I would recommend find the domain and range of the original function, then just switch them. Sound easy? Do you guys remember interval notation? For example, like if I have y is greater than or equal to 3, how would I write that in interval notation? Okay, it'd be a closed bracket 3, and it's going all the way to infinity, and then I close the bracket. Okay, so I just wanted to remind you of interval notation. You will see that on your diploma for sure. Okay. Well, at least last semester they used it.
Wait, so closed bracket means that it's
Equal to, yeah. For example, if it was y is greater than 3, you would have an open bracket, 3, and then to infinity. Infinity and negative infinity always have the open brackets.
It's just like x equals any real, and it's just negative to infinity.
Yeah. So I'll just write that out for you guys so you can see it. So say for example, if we have x as an element of all real numbers, then it will be open bracket negative infinity to positive infinity open bracket. Alright, just looking at some transformations. We have an original graph, x cubed minus 2. It's going to undergo the transformations where it's translated 3 units left and 4 units up. Write the equation in terms of f of x. I'm going to actually write it in terms of the equation and in terms of f of x for you guys. Okay, so just thinking of transformations, f of x will now become, okay, let's take a look. We're translating 3 units to the left. So now it will be f of x, 3. What goes in the middle? We're going to the left. Mark? Plus or minus? We're moving to the left. You got it, Matt. Good team. Okay, and now we're moving 4 units up. So on the outside of the function, we go up 4 units.
Isn't it saying though that f of x is equal to x cubed minus 2?
Yeah. So in function notation, in terms of f of x, this is what the transformation would be. Okay, to extend this, I am going to write the equation with the transformations as well. Okay, so f of x was x cubed minus 2. So the transformation, okay, what is the x replaced with? X plus 3. So what's this x replaced with? X plus 3. So we have x plus 3 cubed, okay, minus our 2. That's our original graph, but then we have to move up 4 spaces.
Isn't it cute?
Yeah, sorry. Cubed. So we have x plus 3 all cubed minus 2. Add 4 because we're moving up 4 spaces. And then we want to simplify it. Okay, so we have x plus 3 cubed. And then negative 2 plus 4 is just positive 2. Questions?
Why is there like a -2 in the brackets with the x?
So I just wanted to show like this was the original function.
Okay.
Now if we're looking at the transformation, x is replaced with x plus 3, right?
Yeah.
So this x was replaced with x plus 3, and then the negative 2 is still there.
Yeah.
But I also have to show that I'm going up
Okay.
4 spaces.
Okay.
Alright, the next one, we're given the graph of x squared, and on the same grid, we just need to sketch the graph of the transformation. Okay, so to do that, this is where we're going to use point mapping. I might just, in a second, ask for your guys' help, see how you're doing with the transformations. First thing you want to do, though, is isolate the y equals. It's just a little bit easier to see what's going on. So we have y equals negative 3f of 2x minus 5. Moving that 4 to the other side, we're adding 4. So let's just summarize the transformations that are happening. Okay, the negative 3 is telling us that we have a vertical stretch by 3. We also have a reflection over the x-axis. The 2 tells us that we have a horizontal stretch by a factor of 1/2. Always take the reciprocal for your b value. So we've dealt with our A, our B, let's move on to our C. Okay, our C is actually equal to a positive 5, so we're moving right. That's a horizontal translation, right, 5 units. And lastly, vertical translation up 4. So you're probably wondering, like, why did I skip a space here when I was doing the vertical stretch, the A parameter? Like, why didn't I just go vertical stretch by 3 and then reflection over the x-axis? I just wanted to remind you guys the order of transformations. You always do your stretches first, then your reflections, then your transformations. So if you have a piece-by-piece transformation question that you're dealing with on your test, make sure you're always remembering that. Stretches, reflections, transformations. And if you have to write that down, then do that. Okay? If you're given a question like this, though, I would just point map. So now that we've noted all the transformations, x, y will move to, or transform to. Okay, let's look at all the things that are happening to the x. We have a horizontal stretch by 1/2, and we have a horizontal translation 5 units to the right. Okay, so x is going to be stretched by 1/2, and if we're moving right, that means we have to add 5 units. Vertically, we have a vertical stretch by 3. We're reflecting over the x-axis, so this needs to be a negative. And we're moving up 4 units. So once we have our point mapping down, we just need to find a few critical points. Looks like we have 0, 0. Okay, when I did some of the point mapping, they're just funny numbers, -1 and 1 and 1 and 1. They worked out to be decimals. So if you want, you can do those points, or we can just go to the next set. Okay, we have 2, 4, and negative 2, 4. Now, if this was a shape other than a parabola, I would recommend point map each point that you see is critical. Like they've highlighted, or we have highlighted, all of these critical points here. Okay, if it was a shape other than a parabola, point map all of them. But we know the shape of a parabola, so if I take 3 of them, then I can get the general graph down. Okay, so 0, 0. Okay, I'm subbing in 0 in for this x, so 0 plus 5 is 5. I'm subbing a 0 in for this y. 0 plus 4 is 4. Okay, looking at 2, 4. 2 times a half is just 1. 1 plus 5 is 6. 4 times negative 3 is negative 12. Negative 12 plus 4 is negative 8. Okay, negative 2 and 4, where will it transform? Let's find out. Negative 2 times a half is negative 1. Negative 1 plus 5 is 4. And then I've already done this value for y. Y was 4, and it worked out to be negative 8. So if you want to double check, 4 times negative 3 is negative 12. Negative 12 plus 4 is negative 8. Alright, so we have 3 critical points, so we can now plot. We have 5, 4. Okay, 6, negative 8. And 4, negative 8. Who can tell me which direction the arms will be going? Down, because we had a reflection over the x-axis. Good. And another thing to think about was 0, 0 was our vertex, so the new vertex is at 5, 4, which was right here. Okay? So that's how we can use point mapping to transform a graph. This might be useful as well if you're asked to figure out if a point is on a certain graph. You can use the point mapping. Domain and range, let's just practice using our interval notation. Okay, so for domain, who's got it? Leah? A little louder. Good. Negative infinity to positive infinity. Okay, and for our range, what's the highest point? 4. Good. Okay, that's where our vertex is. It's going to be smaller than that. But is it equal to 4? Yep. Yep. It's definitely touching 4. So it's going to be close. Because we're going down, it's going to go forever to negative infinity. And where is it going to stop? At positive 4, and it will be a closed bracket because it was equal to. Okay, so the range is negative infinity up to 4. For y is less than or equal to 4. So it's important to understand all the different types of reflections. So in this question, you're given the domain and range of a function. You don't know what that function is, but you have to utilize your knowledge of point mapping and how the graph will change to find the new domain and range. So let's just summarize. If I have, in comparison to y equals f of x, that's what we're starting with, and now I have y equals negative f of x. Emily, what kind of reflection? Good. So we have a reflection over the x-axis. So just to review point mapping, if we're reflecting over the x-axis, then the y values need to change. So xy will go to x, negative y. So will anything happen to the domain? No. But what's going to happen to the y values? They're going to flip. Okay, and so let's just take, we had 6 to 20, but now these are negatives. Okay, so does it make sense that y would be less than or equal to negative 20, but greater than or equal to negative 6? No, these directions also need to change. And I'm just going to draw you guys a little visual. Okay, so the original graph, let's just plot it out here. So for x is going to negative 2, and then all the way up to 8. And on the y, we're going from 6. I might just count by 2s. Okay, so right now, this is kind of a box of where the graph would exist, okay, in here. If that reflected over the x-axis, okay, we can see the domain would stay the same, but the range would go from negative 6 now to negative 20. So if we're writing that as our range, we would say y is less than or equal to negative 6, but greater than or equal to negative 20. Or if you wanted to have the 20 on the same side, y is greater than or equal to negative 20, y is less than or equal to negative 6. So just be careful with questions like that, because sometimes just the direction of where the inequalities are facing can throw you off. Okay, so it doesn't hurt even to draw a little picture if you want. Okay, next example, y equals f of negative x. Okay, this will be a reflection over the y-axis. Okay, will the domain change? Absolutely. Will the range change? No. We're reflecting over the y-axis, so the range will stay the same, domain will change. And if you guys want, for that first one, can you just put only the range changes? Okay, and for part B, domain, only the domain changes. Alright, so our domain was negative 2 to 8. Okay, if we're reflecting over the y-axis, that means our point mapping xy will go to negative xy. Okay, only the x values will change sign. So let's put x in the middle. Before we had it going from 8 to negative 2, but now we're going to change the sign, so it's going to be positive 2 and negative 8. Okay, if it's reflecting over, now it's at negative 8 and positive 2, so it's got to be greater than negative 8, but less than or equal to positive 2. So you just switch the signs of the inequality as well as switching the signs on the numbers. We're doing okay so far? Okay, part C, x equals f of y. What does that stand for? Inverse. Where does it reflect over? Y equals x. So if you want to just remind yourself, it's a reflection over the line y equals x. Okay, you could draw a little picture. So in this one, domain and range switch. Okay, just like with our point mapping, xy goes to yx. So our domain will now be the range. The original range was 6 to 20. So now instead of a y in there, we're putting an x. Okay, and the range is going to now be the original domain. The domain was negative 2 to 8. So now the y values will go from negative 2 to 8. How are you doing so far with those reflections? Just talking about domain and range. Alright. Okay, number 4. This is a question you guys have seen a few times, I believe, on your portfolio. I'm pretty sure on your midterm, on the unit test for this unit. Given the parabola y equals x minus 3 squared, state the domain so that its inverse is also a function. Okay, so maybe I'll draw it first. Okay, we have a parabola, x minus 3 squared. That's what it looks like. If I were to take the inverse, here I started at 3, 0. The new vertex will be at 0, 3. And it will look like this. So if I have an inverse parabola, like this, and I did a vertical line test, it's not a function. Therefore, what this question is asking is, can you restrict the domain on the original parabola so that its inverse is a function? So let's just go through this visually, and then we'll talk about it after. So here's our parabola. How can I make the inverse a function? I need to remove one of these halves, right? So let's say at the point 3, 0, I took away this left half. What is the domain? X is greater than or equal to 3. Or let's draw another one. Okay, at the vertex 0 or 3, 0, what if I took away the right hand side? I could have a domain of x is less than or equal to 3. Okay, so now if I took the inverse of this, I reflected over the line y equals x. Okay, that would go this way. Okay, sorry if I dipped a little bit too much. Okay, and then if that was reflected over, oh sorry, I did that opposite. Yeah, it would go this way. Sorry. Okay, so the inverse is just one piece, so it would be a function. The inverse is just one piece, so it would be a function. Okay, so basically you're just restricting it to half of the parabola. So the main thing you need to identify is what is the vertex, okay, and then whatever that value of x is, okay, either take to the left of it or take to the right of it. I might just put an option here. What if one of your multiple choice question options were x is greater than or equal to 4? Could that be a potential solution? It can. Because what it's doing is it's taking this piece from the parabola and leaving out all of that. So if you take the inverse of that piece, will it be a function? Yes. But would x is smaller than or equal to 4 be an option? Let me draw the parabola again. Vertex is at 3, 0. Here's 4. This is smaller than or equal to. If I take the inverse, there's going to be an overlap, right? Right there. So this one would not be a solution. So just be aware, the easiest one, if you're asked, would be, okay, taking the halfway point. But there's potential solutions where it's not exactly at the half. So I just wanted to show you guys that. Okay. Is everyone clear? Yeah, I guess we answered that question. I was thinking we would do the inverse too, but do you guys want to do another inverse one, or are we okay with switching the x and y's and then solving for y? We're good? Okay, we can move on then.